All right. So first of all, how's the homework going? You looked at it. Good. That is the first step to doing it. That is not the only step.
Second steps.
The second step is doing it. Some would argue that's the hardest step. Okay. So do have a look at it sooner rather than later because you want to ask a question. You will have questions. I was just talking to Garrett, who asked me a question earlier today. He was talking about how the black body function in the very first question. Just go ahead and look in the notes. So I provided the black body function, and it even says the word black body in the name of the slides that are important. Okay. So the first question, pretty straightforward. It's just plotting something and figuring out what you're looking at. The second question is about whether or not the sun could have been powered by light bulbs. And that is about using the definition of power and energy and area. So you'll look for the definitions of things like flux and luminosity and making sure that you understand those, right? And as we go through them, there are 6 questions, so it looks like a lot of work. But each of the individual problems is significantly more straightforward than have been in previous weeks, right? So I don't want you to feel like you're overwhelmed when you're doing the homework. And if you don't start it, you will feel overwhelmed. When you start it, then you'll feel have you started the homework? Oh, you started it.
I started to conceptually look at it.
You've looked at it, yeah. You did step A.
Well, I tried most of them and I just like thinking about it.
That's okay. I was just telling him that it's better to start this one early. There's more. But they aren't hard. Good. Okay, so we were talking about atmospheres. And we talked about motion of the atmosphere. And now we fully understand why there are stripes on Jupiter, right? Why are there stripes on Jupiter? Draw the. This is such a shitty marker. Did I steal the wrong marker? Oh, is it in here? I have more in here, but they're bad. This is a red one. Oh, here's another. Oh, it's a purple one. All right, we're gonna see what's the best one. Okay. Why does the atmosphere have motion? Yeah. So what causes the cells to start moving? Good. Where is it the hottest? Good. So this is the hottest point. What's the coolest point? What? Yeah, the poles, right? Assume that it moves perfectly. Good. So now the atmosphere does what? Goes out, correct? And then goes away. And then come back down. Okay, and then it goes back in. And those are called atmospheres. Good. And why do they move? Let's say that I'm looking down on the planet. Here is the first Hadley cell. Why do they move left, right? Rotation of Earth. Good. So rotation gives winds. Specifically, trade winds. So sometimes they're going this way. Oops, and that goes throw it backwards. Sometimes they're going this way, away. Sometimes they're going towards. Right? Okay. That's what we use to navigate on the surface. So why? This is the Earth. It has 1, 2, 3, 1, 2. So that's the Earth. The Earth has 3 in the northern hemisphere. Why does Jupiter have so many stripes? What? Moving along. It's rotating faster. Faster rotation. More Hadley cells. Is that always true? No. What planet is spinning just as fast as us that has less Hadley cells? Mars. Mars has how many Hadley cells? Yeah, 1 or 2, depending on the season. What's the difference? And older is really important, right? Because if you have less energy to make it go up good, right? Then you're not going to have any of this motion. This motion is all happening when you have an adiabatic gas that's rising, right? And then it's able to get rid of the heat. But if the atmosphere is very thin and there's not a lot of energy to get rid of in the first place, then potentially you can get it to rise. But before it gets into convection, it just gets rid of it through radiation. Right? Okay, so not a hard and fast rule, but generally true. Okay, so now let's talk about the greenhouse effect. So we like the greenhouse effect, believe it or not. We don't like climate change, but we would be dead if not for the availability of greenhouse. Okay. So Venus is famous. Venus spins very quickly or slowly? Well, how fast does Venus spin? Compared to the year. Good eye. That's right. 1 to 1. The Martian year or the Venusian year and the Venusian day are about the same length. Okay. So do we expect lots of Hadley cells? No. Do we have lots of Hadley cells? No. But it's hot. Why not Hadley? This didn't have anything to do with it. This had to do with the adiabatic transfer of heat. It's rising due to pressure. It's very hot everywhere, right? The whole surface is very hot. Okay.
Because we have poles like we do with it on paper.
Yeah, there's like a strong dichotomy in the temperature profile here, right? But the biggest temperature difference for Venus is the day-night temperature difference, where it's like 40 degrees cooler. So in fact, this, instead of going from up, it mostly goes to the left, and it drives super winds at the top of the atmosphere. Really fast winds, really high up. But at the surface, you have almost no wind at all. Okay. So how to get that way? Venus probably, this is a big probably. So I would hear lots of arguments for and against this. So we assume that Venus started off the way we did. That is potentially a bad assumption. Right? Why would that be a bad assumption? Well, I mean, so let's imagine. I'm going to give you a circumstance, and then you'll tell me whether or not this is fine to assume. Okay, the Earth and Venus, they form in a similar part of the solar system. We don't know whether or not they migrated. We don't know whether they moved in. We do know that Jupiter moved. We know that Saturn moved. And we know that Uranus and Neptune switched places as Jupiter and Saturn got closer to the sun in something called the Grand Tap. Okay, so Jupiter and Saturn moved towards the sun, fell into resonance, and disrupted the entire solar system. And you see evidence for that in the late heavy bombardment, which is recorded in the surface of the moon. Got smashed by a bunch of shit. Okay. We don't know exactly where Venus formed. We have estimates. Okay. We think that it's made of the same stuff that the Earth is made of. That is to say, it's neutrons. So we say that after it formed a surface during the late heavy bombardment and was hit by a bunch of icy asteroids, that water was still. This is the prevailing idea. Is this a bad assumption? Right, so remember 0.7 is closer, but it's not super closer. The reason that we think of Venus as so hot is because of its annoying atmosphere. It's right on the edge of habitable. So if you remove the atmosphere today, you put Earth's atmosphere and Earth's water would be liquid. Not too hot currently. It's only when you add greenhouse gases that it runs over. You want to know how much the solar radiation goes up by? How much hotter it is at 0.7 versus 1 AU? What? No. So what I mean by this is here's the sun, here's some distance d, Venus, and then here's some other distance d2 to Earth. This one is equal to 1 AU. This one is equal to 0.7 AU, approximately. Here, the flux from the sun at Earth is some number. Here, the flux at Venus is that. How are they related? What's the definition of flux, by the way? That's the luminosity of the sun. That's not going to change. The distance is the only thing that's changing. And it changes as they go away. So it gets hotter as they get closer to the sun. That's so I can actually create a ratio of these. The flux at Venus divided by the flux at the Earth. And that's just going to be L sun over 4 pi 0.78 quantity squared over 4 pi 1 We'll do that. Whatever range is it. Right. 4.5. Mm, 7 squared, it might cancel out the 80. Good, so what's that number? 0.4. On the bottom? Yeah. And then 1 divided by that? 2.04. So it's twice as hot. That means. You may need this. That might be useful. That's not arbitrary. Okay. So it's twice as hot, but we said that without greenhouse gases, we would be freezing. Right? So maybe it's the case that Venus started off warm enough to have water. This is not a bad assumption. It's just kind of an unscientific one for me to simply state. Because there is no way for us to know. Right? On Earth, at least we can pick up rocks, old as fuck rocks. And we can figure out what they're made of. On Venus, you can't pick up old as fuck rocks because the whole surface overturned. When? 600 million years on, every rock on Venus melted. Right? So good luck. Right? The only place you'd be able to find an answer to this is the Earth. I mean, it could be Earth, but it's very unlikely. Oldest meteorites we have on the Earth are not 4 billion years. It's not. Okay, let me clarify both those statements. There are very old meteorites that we have found on the Earth. I need to clarify that statement, but they're not of parent bodies that are planets. I think the oldest Martian meteorite is like 4.4. Which maybe that's old. Maybe that's old. We haven't found a Venusian meteorite. But you could look for them on the moon. Because the moon stopped being geologically active right away, right? Within 1 billion years. And there are some places that were inactive right away, like 4.4 billion years ago. And shit just sat there. And what you're looking for as you walk around on the surface of the moon is for a rock that has color when everything else around you is gray. And the geologist's wet dream. You just walk around, picking up a little dust, right, as you walk, because it's super dusty there, and you're looking for anything that's a rock. And that may be a meteorite. Okay, so that's probably the only way we test this. Right now, it's what we have to do with, right? It's what we have to base this on. And it doesn't really make sense to think that any other way because we don't have evidence to the contrary. So it's not a great assumption, like scientifically speaking, but it's what we, and you'll notice that a lot as you progress. Right away, Earth and Mars have a substantial greenhouse effect, right? And let me just ask this question, look at a quicker question. Which constituent of the Earth's atmosphere makes the largest contribution to the greenhouse effect? You read the answers, and then you let me know with 1, 2, 3, 4, 5. Or A, B, C, D, F. Wait. A, B, C, D, F. Okay. Okay, put your hand up when you're ready. Let's vote on 3, 2, 1. How many fingers is that? Good. Carbon dioxide is the one that everyone yells about. Trick. It's a trap. Why? Well, no. This one is important, but it obscures what's doing the most damage. Water. But you can't get rid of water in the atmosphere. So watching water go up or down in the atmosphere is hard. Watching carbon dioxide, which is only made by a limited number of sources and doesn't occur naturally outside of those sources, different. So water contributes to greenhouse gassing, and when it gets hotter, is created more. Steam is a great greenhouse, right? So this one is very hard to disentangle the cause and the effect, whereas this one contributes directly to the heating without creating more carbon dioxide when you do it. So we use this as a metric when this is the most important. This one packs a huge punch. Pound for pound, this is the best at doing its job. It's just not very fun. This absorbs heat. It's okay. It's not great. This we don't really have a problem with, and this one barely. Okay. Okay. So let's talk really briefly about the greenhouse effect. So you notice our good friend, beautiful friend. What's this? Kind of like area of a circle. Looks like the area of a circle. That's all it has. Area of a circle is here, right? This is the surface area of a sphere. Okay, what's this? Good, but what's this? The flux, right? Because we said something like the flux is, remember this? What? Sigma t to the fourth. Right? And then if I put over here L over 4 pi r squared, right? The ball. Okay, and you can look at the derivation for how we get 16. But the interesting thing is that most of this doesn't change, right? 16 doesn't change the distance, as far as I remember. And pi doesn't change the distance from the sun, and sigma doesn't change the distance from the sun, and the luminosity doesn't change, right? It's only the distance. So I can turn this into the temperature at the Earth, and then how far away I am in AU. Right? And so the temperature is going to go up. If this number is smaller than 1, then this thing gets bigger. This thing is bigger than 1, this thing gets smaller. Good. That's the greenhouse effect in temperature. This is too cold for us to live. We would die. Right? Terrestrial planets emit most of their light in the infrared. That makes sense. If we had a visible planet, that would be a molten planet. Right? That would be magnetic. So they're mostly brightest near a wavelength around 10 microns, which is over here. So this is this here. This is where most of the radiation from Earth comes out. This is the stuff that we get. And you see on the left-hand side here how we're missing. So this is the stuff that the sun produces. And we're missing all this. You know why that is? Let me show you how to read this. This is the percentage of absorption and scattering. If it's at 100, that means nothing gets through. If it's at 0, it means everything goes through. So at the very top here, none of the ultraviolet makes it to the surface.
Because it's being blocked by the atmosphere.
Yeah, which parts? Think about them, right? So you can see the constituents, right? Ozone does its fucking job, right? Keeps us all alive. Good. And there's this little thing called radiant scattering, but we're not gonna worry about it. That's what makes the scattering. So ozone comes in, bounces, and then eventually gets absorbed by. Okay. And you can see methane here. Little insidious bastard. Okay. This thing's it's gonna how far it's trying to warm up the world. Very good at its job, but it only does it in a couple places. Carbon dioxide has these big bands. These are locations where it does a lot of absorption or scattering. But mostly in the infrared, right? There, a little bit in the visible, but not that much, right? This little dip, right? Probably contributed a little bit. Who's the asshole? Water. It's just like, what the hell, man? And even these gaps here, they show up, absorbing visible light. So not only are they over here sucking up all of the infrared, they're sucking up visible light, and they're getting all hot. What an asshole, right? We love drinking it. It's making us so warm. So I propose freeze the earth. So here's the added contribution, right? So we live here in the visible, and we see because this visible light makes it to the surface. Right? What you'll notice, there's plenty of space here. A lot of animals, they can see that part. We chose to see here. That's where the peak of light comes from. Couldn't choose broadband eyes. You have to choose narrow, good eyes. Okay. And then over here, you have something called the infrared window. And this is like a little hole in the water vapor. And that's like how some heat gets out, but not all. You can see a very interesting problem. So if you recall from your black body equations, the temperature, here's your black body, right? The location of the peak has to do with the temperature. And as the thing gets hotter, what happens to that peak? What's it? This is the black body curve. So this is intensity as a function of lambda. So over here, blue. And over here is red. So as I make something hotter, yeah, it actually turns this way, right? It doesn't necessarily go up or down. It can change the shape a little bit, but we're not going to get into that just for the purposes of this, right? You would have to plot the curves and show that all the curves go on top of each other. We're not going to do that. So the main thing is that the T goes to the left. Now watch what happens if I start with something like the blue line. Okay. The blue line, this is well centered so that a lot of the emission gets out. What happens if I heat the thing up? Just to the purple line. And look, now some of the heat, right, is being blocked. So you're peaking over here, but you're blocked. As I keep moving this purple, you can move it potentially into this region where there isn't that window. How the heating gets trapped even more. And this is the contribution to the runaway. Water vapor is alone responsible for. Okay. Okay. Oh, fuck. Things talking about no. Talk about that too much. Yeah, I already said all that. Too much, yeah. Okay.
All right.
I said all this. Okay. So if there's liquid water on the surface, greenhouse effect is self-stabilized. How does the water carbon cloud cycle work? Take 2300, you do not know this. If you are listening to Astro 1000 this semester, you will know this. It is absorbed, carbon is water soluble. Okay, here's my rain cloud. So good, draw your raindrops. Okay, CO2 was in the atmosphere. This was CO2. And then it gets put into rings. That goes to well, plants. Water. Water rolls off to the water. Yeah, I mean you're 100% right that plants do eat. But before you had plants, you still had CO2. And this goes to ocean. Okay. And ocean takes the CO2, it's now mixed in, it's called dissolved CO2. Fish love dissolved CO2. Plants love dissolved CO2. Right? It uses that in order to make its body big and strong. And then what happens to the CO2? Yeah, it sinks again. Sinks again and forms what kind of rocks here? Right? What was the bigger word for that? In between sedimentary and limestone, you call them what console was frozen in? What? Carbonates, yeah. Carbonates. Yeah, turns out this is super good, right? So you start with atmospheric CO2, you precipitate it with water, it's water soluble, loves being in water. They come streams, almost all streams go out to the ocean, there's only a few exceptions. And then they sediment, takes a long fucking time, but don't worry, we got geologic time scales. They become carbonates, but now they're just rocks. I want them out of the atmosphere completely, I don't want it to be grind up this rock, so now where do they go? Ah, they go back into the earth. So here is a carbonate rich. Here is a rocky mountain. Let's call this the Andes. This is a trench. This is subduction. And now carbonate rich material back. Okay, now it comes out again. What does it come out of? Ah, that was good. So good thing I wrote this as the Andes because now I can make it explode. Okay. So let's say there's a volcano. What comes out of the volcano? That's correct. What else? Yes, you're both right. What I mean for gas? Carbon. Okay. So this is the CO2 cycle. And it's really important because you notice that technically we don't have any life. Right? And I'll talk about how life modifies it, but it doesn't require life to start. And in fact, we did not expect life when the CO2 cycle was working. Now it takes a long time, don't worry about it. But what you need is this. You need the ability to put crust back into the mantle. You need liquid water. right? Because otherwise you cannot scrub the atmosphere. Okay. So now we get this really beautiful diagram. Okay. This is. Have you ever seen a temperature gauge that is not up down one? That one looks like a needle. Okay. So this is just right. Hold it on stop. Okay. This is too hot. So what happens when it's too hot? What? What overheats? Yeah, from a carbon perspective, right? Like look at the whole system. And tell me what happens when the atmosphere gets too hot. Water evaporates. Very good. And that produces? Good. Good. And that produces? What does water vapor do when it rises? Good. Okay, so let's increase the number of clouds. Okay, and now CO2 starts raining out very quickly, very effective. I scrubbed CO2. I put it back in the ocean, I subduct it, and the clouds cool the atmosphere in two ways. What's the first way? I just told you. Rain does what? Yeah, good. Reduce CO2. What's the other way that it cools the earth? Flex. Flex. Good. So it gets too hot and the clouds are formed and then it cools. Okay, now let's let it get too cold. No clouds. What?
Can't reduce the CO2.
Can reduce the CO2.
Less rain.
Less rain.
More sunlight comes through.
More sunlight comes through and it's being absorbed by more CO2. Does not being scrubbed. Right? So absence of clouds leads to more CO2 and an absence of clouds leads to
More sunlight.
more sunlight. And also, what is the compare the albedo of the Earth without clouds to the Earth with clouds? Does Earth absorb more light with clouds or less light with clouds? It absorbs more, right? Think about it this way. Clouds are white, fluffy, and nice, reflective. Ocean is dark and blue. Yeah, deep and ominous and scary.
Cloud, nice and fluffy.
Okay, so in fact, it absorbs more. Okay, and then it cool. Too cool, clouds condense out. That creates more CO2 because they're not scrubbing. And the sunlight gets absorbed, so it's better. Okay. So you say to yourself, well, good, we solved the climate crisis, right? Why not? Yeah, because that's cooling for us. How long does this take? Not so bad. Not so bad. Not that good. I wish 6 months ago I would be like, fuck it, go on vacation or something better. Wrong order of magnitude. Million was too big, but day and hour and months are way too small. Okay, little higher.
10,000.
Right order of magnitude, it's about 40,000 years. To stabilize. Okay. So if it gets too hot, it takes about 40,000 years to cool off. If it gets too cold, it takes 40,000 years to heat up. Okay. So that's why it's not gonna help us in the short term.
Will it fix itself though, in like another 40,000 years?
If we all die. Yeah, certainly. And certainly we will all die. I haven't yet figured out how to live forever. So sorry, that's not what this class is. Okay, now you get it. If there's liquid water on the surface, the climate cycle can be self-stabilize. Likely at Venus, you know, one of the first things you said was like it gets hotter and it gets hotter, it's starting to be pretty steep, right? So what if up here you can't form clouds? Okay. So we talked a little bit about the Clapeyron equation and how much atmosphere can hold a certain vapor product before it gets too much and condenses and falls out, right? And what you can do, if you want to build a planet that doesn't work very well, is you can make it really hot all the way up. That the clouds try, or the water vapor tries to rise, but it doesn't rise enough to cool, and you just have this hot, moist fluid near the bottom. That's contributing. Now, eventually you need to get rid of the water. You know how to do that? I know it's but what?
Radiates on.
What do you mean radiates off?
We didn't talk about it tonight. Where sunlight breaks the bonds of.
Right, so we talked about that in the context of Mars, right? So this is why Mars is red. The surface is oxidized because the surface is rusted. There's a lot of hematite on the surface, which is iron oxide rocks, right? So the color of Mars is a testament to the fact that water was broken apart and the hydrogen being light escaped through a process called thermal escape or Jeans escape. And we'll talk about that shortly. Likely on Venus, the same thing occurred. You got water high enough. Right, remember we have to draw a picture. Venus's atmosphere. Here's altitude. Here's hot. Hot. Calm. Okay. And then let's follow the path of a lone baby water. Okay, it's trying to live its life in unrelenting heat events. So here it's very hot. And it rises. It goes up. It's cooling. Finally, gets high enough. Now what's happening? It should connect, but now it's getting salted. that? What? UV, very rude and perfectly colored ultraviolet radiation. And what happens to the little poor water here? My little H2O? What? Plus gamma, you know, gamma means light. H2O plus energy equals. O plus H plus H, or OH plus H, or that is a dissociation reaction. I broke something apart. And now the oxygen is like, oh, chill, I don't even care, never even liked hydrogen. And the hydrogen's like, okay, why does the hydrogen go up and the oxygen doesn't? Oxygen's heavier, and the same rules still apply. In fact, they apply to individual molecules. So hydrogen is very light, and it feels a force. You go up, you dumb idiot, and everything else feels a force downwards. Now, of course, it's supported by gravity. But if I can liberate hydrogen high enough, then I make it to the top of the atmosphere, and I just give it a little punch it. This is thermal escape. Or genes escape, not like these. Human being. Okay. Does that make sense? Ultraviolet light. Association. So that's what we think happened to Venus. I guess we'll find out. I said that there's the solution. You can create carbonic acid. Yeah, we didn't even talk about life. I guess we should talk about that. There are ocean-dwelling organisms that create calcium carbonate. There's a lot of liquid water. You lock it up in carbonate minerals, and that's like Earth. The question is, somehow the lack of liquid water let CO2 remain in the atmosphere. Now, if we go back to that original assumption that Venus had water, and you just remove that, right? How does it affect this? Boom, just right away, right? And so it doesn't even matter, right? Okay. This is carbon. Well, I guess this is from 2009, so it's probably not as good anymore. But this is the super sophisticated diagram, right? Boxes with arrows. Okay. So basically the idea here is these is showing you how they're contributing per year, right? And this is the amount in grams, and then it's showing you how much heating per year. And pentagrams of C of carbon. Sorry, not heating. The atomic mass of C. So the biggest contribution here is it oil and gas? All these numbers. No. We should be able to have a little drag strip and drive and fly to our favorite places, right? That's not the biggest issue. What's the biggest issue? Yeah, oceans and plants, right? Oceans and plants are putting a lot of, oh wait. Here they're putting it in, right? They're the worst offenders, 200 in. They're also taking close to 200 out. So they're like net zero. So it is oil and gas. So it's very easy to look at a situation like this and say oceans are the real problem, they're outgassing and there's degassing going on from the top of the atmosphere, the top of the oceans, right? So degassing is just when dissolved gases in the water come back out. Right? And similarly, plants that are decaying, they produce methane, they produce greenhouse gases. And it's easy to point at permafrost and say, oh, like that's the issue. But there is absorption by plants, right? And that offsets a lot of those issues. So net, these contributions, right? And of course, this is a suck. This removes it forever until you get out. Net, it's this. You ever seen videos of the Earth breathing? Okay, I'll show you. I'll show you. If our folks who haven't seen that, I'll pull that up when we're in between slides here. Okay. I said all that. Oh yeah, that's fun. Sterilize the Earth. Okay. Come on, why does it not like to click? We talked about fossil fuels. CO2 is currently entering about 10 times faster than the oceans and rain can dissolve it. That was in 57. 1957. Things have changed. So, CO2 that is dissolved accumulates faster than it can be converted into carbonates. One thing to remember, we talked about the Clapeyron equation that talks about the ability to saturate a fluid. So one thing that you have to remember is you can only put so much of something into a fluid before it dissolves out, right? Similarly, you can only put so much carbon dioxide into water before you change the composition of the water significantly. So you are literally acidifying the ocean, not you personally, but us as humans, right? And that's not so good. Turns out that corals really don't like being swimming in acid. Okay. Oh yeah, that's it. So climate models can exchange the temperature increase. We don't know what the stable natural balance will be. Pretty bad. Here's CO2 and global temperature. And remember, why do we use CO2? Well, that's because we want to distinguish it from the water vapor, which is contributing directly to the increase in water vapor happens with the increase in temperature. So those are always correlated. But in this particular circumstance, you can see in the 1200s and 1700s, it actually got cooler. And on the left-hand side, you see the concentration of CO2. Now, how do we have measurements that far back? Exactly correct, right? So we have measurements of the temperature and we have measurements of the CO2, and they don't always correlate. And only currently do they correlate, right? Because one is driving. And if you draw that, this is when you really start taking measurements good. Whoopsies. Okay. All right. That's not fun. Cool. About half of the CO2 increase since the 1800s has been dissolved in the oceans, and it has reduced the pH. Remember that pHs that are small powers of hydrogen, that is acidic. pHs that are high, those are alkaline, right? So turns out fish don't like that. Corals in particular don't love that, and corals in particular are important, not just pretty, because they do. What corals do? I think about a movement, that is what? What does it mean flows inside? Creating oxygen from correct. And here's your biology lesson of the year. Biology lesson. Okay. CO2. C O CO2. uh, goes into a cell. What's that? There you go. Oh, here we go. That's how you know it's a cell. Okay, and then it gobbles it up, and what comes out? O2. And where's the seed? Makes its body. So why is it like, okay. Why is it really good to eat like celery and like lettuce if you have constipation? Fiber, very good. And fiber is another word for what? Almost, you're getting there. Cellulose, right? No, that would be fructose. Cellulose is like the structures. So cells build little structures, and they're like long, thin filamentary objects that are fibrous, right? So eating a lot of fiber, now of course that's all built of carbon, if you're talking about, right? But the reason why there's these long strings of cellulose in your food is a photosynthesis. Okay, so in photosynthesis, you have corals. They do that in the water. They take in CO2. They give us oxygen. They are fed up. They're dying. They can't live in acidified oceans. Deforestation also happening. They're dying too. Okay, everything's dying. Good. We think that Earth is unique. We don't know. We know that there's basically these two things. If we found them on another planet, we would call them biomarkers. Lots of folks right now are focusing on this biomarker because they're looking at extrasolar planets, planets outside of our solar system, and they're seeing molecular oxygen, and they're wondering whether or not there are ways to produce this abiotic. Can you produce this without this? And that's not always clear. So places where you don't have life, what are our two neighbors who don't have life? Mars and Venus, what's the composition of their atmosphere? How much? Yeah, 90+%. I would say like 96, 97% CO2. So when you get home tonight, you're going to look up the great. Spell that on. Great oxygenation event. Okay, when we went from CO2, O2, N2, X. We killed everything that breathed CO2. One of the, now not really a major mass extinction in the way that we think about the 5 mass extinctions, but the question is, can you build an atmosphere that has O2 in it, even in a trace amount, in non-biotic ways? As for example, if we look at something like Mars, Mars has ozone. And you might say to yourself, well, what the heck? That's just an extra O. How did you get ozone? But it does that through chemistry of water, not O2. Whereas O2 becomes dissociated in the upper atmosphere of the Earth, and then 2 O's see 1 O, and they become friends with 3 O's, right? That's how ozone is made on Earth. So ozone chemistry on Earth and ozone chemistry on Mars, completely different, right? So the presence of O3, not a biomarker. Presence of O2, okay? We won't be able to grab these. We can grab them in the solar system. So if, for example, we landed on the surface of Europa, right? Europa is famous because it's got an underwater ocean, right? Underground ocean. So let's say we land on the surface and a little robot comes along and picks up something and chemically analyzes it, and it looks a lot like carbonaceous mineral. That'd be weird. But it'd be super weird. Why? Well, remember that this is all happening under an ice thick sheet. Yeah, maybe it came after a crack. I don't know how. Where do you know that? Just imagine. Because I don't have to burrow 15 kilometers down to get it. Could all of this happen in here? Yeah, you could have volcanoes down here, right? Like seafloor vents spewing carbon dioxide. And then, in order for it to be livable with oxygen, you would need what? Yeah, you need little fucking little doodads, right? Little stuff that turns it into carbonates. Whose dead bodies contribute to carbonates. Now, is that the only way to make the carbonates? No. But would we lose our shit if we found some carbonates on the surface of Europa? Yeah, you bet it should. Okay. Wallace, you know what those are? Just also don't say that, right? Some of my best friends are. You never see Marcel the Smell? What else are mollusks? Not just snails. Clams, oysters, right? What do they all have in common? Shells made of? They're making their bodies from the stuff that we put out of the cars, right? Okay, this is why you should eat oysters. You know that oysters are the only renewable seafood that actually improves the planet? Now, you are eating them alive. So I understand this very well. What? Okay, all right, sure, relax. Just talking broadly here. Okay, we just found rocks on Europa. Okay. So these produce a lot. On the Earth, they are the leading producers of carbonates. Now, not oysters, but other bugs. Diatomaceous. Okay, not as fun to say, but you know. Does that make sense? Okay, so before we switch over, I promised you let's look at the breathing Earth. Oh shit, how am I gonna do this now? I need to mirror. Oh God. Oh Lord Jesus, baby Jesus. Okay, will this work? Breathing Earth. Yeah, someone has to be my eyes over there. Let's go to what?
Where you go?
Let me put in more letters. Images. Okay, that's the ice caps. I don't care about that. That's not a video. Oh, so cool. That's ice caps. Okay, wait. This is why you prepare ahead of time, Prismani. They like get rid of this already from the internet. Yes. How come I can't click anything in this life? I know, but I should be able to. Is this one of these open in a new? Yeah. This one? Pretty good. Yeah, it's okay. I'll explain what's happening. Okay. So this is nice. This is from you remember that big snowstorms that we got? Like all of California was snowstormed up. So this was like early last year, I believe, and then this is us down here. And what's really cool is this is monitoring CO2. So you can see who's that? That's us. Who's that? San Diego, very good. So we're producing a shit ton of CO2. Surprisingly, I don't understand this one. You know, San Francisco like looks like pretty good, kind of sexy. And so their CO2 is getting sapped off and probably put it in the acidifying ocean, by the way. Okay, but look down here. Who's that? These fucking assholes, right? So you got something like Houston down here, just outgassing, and this video is not video, but what you can see is it gets swept into the atmosphere, and we can track it with satellite data, high resolution satellite data that determines where the CO2 is and who's emitting it. So you can go down to the data, and what you'll notice is right. So like this is the coast, but like you have this plume, right, that comes off the earth, and of course it's like mixed in with the atmosphere itself. So as it flows and ebbs, you watch it move off. I'll find the other one for next Tuesday's class. But what's really cool is that we watch it in the same color. And in this video, you can see how places that have forests, right? So currently all of this region here, it's all forest, but it's frozen. So it's not doing a lot of exchanging, it's not doing photosynthesis, right? But if we look down at the southern hemisphere, what you would notice is you have these huge like clouds basically get sucked into the Amazon and then disappear. It's a literal sink. It's like grabbing it from the atmosphere. And similarly, you would have like in the southern hemisphere, you have in the southern part of the US, off of here, you have like large regions like Sargasso Sea, which have a ton of phytoplankton, and they'll like swallow up the CO2 and burp out a ton of oxygen. And so it's really cool because they'll color them in two different colors. They'll do CO2 concentration in orange, and then I forget what the other color is, like blue or something. And so you'll see this breathing every day of the oceans in that. Cool. Okay. I went a little bit longer than I wanted to there. Didn't get quite as far as I wanted to there. We want to talk for 5 minutes about Jupiter, or do we want to do the SOTIs?
This is important.
Don't give me that.
And
Oh, really?
the same thing. So, that might be different.
Okay. It's in 6 days. They keep emailing me to tell you. So